we have actually a space that we say that distance between x and y equal to 1 when x is not equal to y. Let's prove that this is a question that let's prove that distance, if we define distance between x and y like that, distance of x and y is 1 when they are not equal, and distance of x and y is 0 when they are equal. Then prove that it is a metric space and it satisfy all the condition of metric space in real analysis. So let's come on it. So we know that the distance between x and y equal to 1 in case of x is not equal to y. So first condition, we have to check that distance of x and y is greater than equal to 0 when x is not equal to y, and distance of x and y is equal to 0 when x is equal to y, which is the same condition that is written above. So in that, distance is greater than equal to 0 because it is 1, greater than equal to 0, distance is greater than equal to 0 when x is not equal to y, and distance is equal to 0 when x equal to y. So we have reached at that point. So first condition is satisfied. Let's check the second condition. So what is the second condition? They said that distance of x to y equal to distance of y to x, which is also equal to 1. So second condition is also satisfied because when x is not equal to y, when x and y are not equal, then distance between them is also equal to 1. Okay, now let's come on the third condition. What is the third condition? That is the third condition. What is it? Let's come on it. Okay, so in the third condition we are going to discuss what we are going to discuss that distance. Let's take case 1 when x is not equal to y, and we have introduced another point as z. X is not equal to z and y is also not equal to z. So when x is not equal to y, then distance between x and y is equal to 1, and distance between y and z is also equal to 1 because they are not equal. Distance between x and z is also equal to 1 because they are not equal. So in that case we have to prove what? We have to prove that distance of x and y is less than equal to distance of xz plus distance of zy. So let's check it. So what is the distance between x and y? It is 1, and their distance is also 1 plus 1, it will be 2. 2 is greater than equal to 1. This is true, so this is satisfied. Now take case number 2. Let's take case number 2. In case number 2, so when their distance of when x equal to y, y equal to z, and z equal to x, so then distance of xz is equal to 0, distance of xy equal to 0 according to the definition of the metric. Distance of yz is also equal to 0. So we can say that distance of xy is less than equal to distance of xz plus distance of zy. 0 is less than equal to 0 plus 0, so this is also true. So in all that conditions, this is a metric space and this is proved in front of you. Now let's discuss another properties on the metric space. Let's come on other properties. Cover of a metric space. Cover of a metric space. Let's come on the cover definition of a metric space. A cover of a metric space is basically what? In a set X is collection. It is actually collection of open sets U alpha such that, so we have a cover of a metric space is defined as like that. Cover of a metric space is a set. In a set we have a set X, and there are open sets. There are open set. It means that the endpoints are not included in those sets. So each U alpha is open. It means open set. And number two condition is that the union of all U alpha contains S, that is S is a subset of U alpha. It means that those each U alpha is open set. So these open sets are contained in X, and the union of these open sets is a superset of S set. So let's define it again. A cover of a metric space, a cover of a cover of a set in set S in a metric space X. X is a collection of open sets such that each U alpha is open. The union of all U alpha contains S. So it means that open in X. Okay, open in X. So we a set of a S in a metric space is collection of open sets. Is a collection of open sets U alpha. Those collection of U alpha that are open and their union contains S set, then those are called the cover of a metric space. For example, I can give you example, then you will understand it properly. For example, I have S equal to 0 1. Okay, if I have S is equal to 0 1 in the real line, then what we have, then let's try it. Then cover equal to u1 u2 u3. So this is a cover, and it's -1 comma 0.5 0.2 comma 1.2. So these are open sets u1 u2 u3. So if our interval is 0 1, this is a closed interval and this is equal to S. Okay, so this is a closed interval and these are cover of it. How these are cover of it? Because these satisfy the condition of cover. What are the condition of cover? Basically the condition of cover are what are those conditions? So condition of cover are those open sets are open sets. Number one condition, those should be open sets and the union of them should contain S. So let's check it. These u1 u2 u3 are three sets, and these are open. These are open. Yes, these are open. First condition is satisfied. So what is second condition? Does their union contains let's take your union. If you take their union, then we will get -1 0.5 union 0.2 comma 1.2 union 0.7 comma 1.5. So if we take the union, this will be -1 comma 1.5. So does it contain that? Yes, it contains. So it is a superset of S. So it contains S. This means that these are cover of S because These satisfy both the conditions of cover. Okay, let's now go toward the subcover. Let's define the subcover now. Subcover. This is also a basic concept in real analysis. A